L'enregistrement est en cours.
Hello everyone, do you hear me?
Hello, Sophie. Yeah, we can hear you.
Okay, we can wait 5 minutes to let others join. I think we can start now. Hello again, everyone. Welcome to this new reading group session. and thank you for joining us. Today we have the pleasure to welcome Robert Selemani. Robert is the co-founder and managing director of AI S1. He is an AI and cloud practitioner and a master student in data science at the University of Edinburgh. So, Robert, I give you the flower to present yourself, your research, and to start your presentation.
Thank you, Sophie. Just checking if you can see my note taker in the lobby, then you can maybe admit it. If you can see my note taker in the lobby. If not, let me try and edit.
No, I can see.
Okay, just a second. Yeah, it seems like I can't add the the note taker.
L'enregistrement est en cours.
Yeah, it's fine. Maybe I can get the recording from you. I'm gonna. Okay. Okay, apologies for the delays. So, good evening, everyone. As introduced by Sophie, my name is Robert Selemani. I'm from Zimbabwe, currently based in Harare, Zimbabwe. I'm a co-founder of AI Eswatini and the managing director of the organization, which is based in Eswatini. I'm also starting my master's journey with the University of Edinburgh. I currently work full-time at Cassava Technologies and Cassava AI is an AI platforms engineer. So this is a bit about me in terms of my background. I did my undergraduate in informatics at the National University of Science and Technology. So yeah, this is it about me. Yeah, where can we get started? But above all, it's an honor to be with you here and to be speaking and discussing with you today. So maybe I can hand over back to Sophie so that she can set the scene and point us to the direction that we need to take. Thank you.
Thank you very much, Robert. Yes, we can start. You can share your scan.
Okay. I suppose you can see my screen.
Yes, we see it. Okay.
Okay. So the paper that we are going to be focusing on today is my latest publication that was published on the 10th of June in the Journal of Applied Informatics and Computing. I'm sorry, I'm using this offline version. I've been having challenges trying to access the online published version. Right? So maybe just a bit of background as to why this research and where did it all come from. So this was the research that I did for my undergraduate degree. I did this initial research in that was between November 2021 to July 2022. So that's when I was doing my final year for my undergraduate degree. So that was almost was COVID-19 was getting to a point where it was now normalizing and people getting to be comfortable with the new normal way of life. But we still needed a solution. There was no solution in place yet, and we still needed to have a solution. So as someone who has always been wanting to make impact in life and doing things that has a significant outcome, I thought to myself, what is it that that I can do that can lead to a greater outcome? That if I look back after some time, I'll be like, wow, I did this, I did that. So this is the background that led me into doing this this program, this research. I mean, so when I was doing my undergraduate studies, I also had modules on bioinformatics and health informatics, and I found myself naturally enjoying those modules as compared to the other modules that I had in like policy informatics, geoinformatics, and the likes. So I embarked on this journey. I did my undergraduate degree and I finished and I completed and I graduated, right? But I did not have a plan to have this work published back then, right? But then as time went by, with my vision shaping up as to the career path that I wanted to take, with me by the time also working in the healthcare sector between 2020, 2021, 2022, I was working in the healthcare sector, just supporting the IT department. 2023, I moved to Eswatini. I was working also in the healthcare sector as a data analyst. I started developing interest within the field, and I was like, it reminded me of the research that I had done before that was just sitting somewhere in the shelves. And I thought, what if I develop this work further and put it out there? It will probably make a difference. So that's when I started the journey of working on this paper for publication. But coming back again, taking a step back as to how I chose this problem statement in the first place when I was doing my undergraduate. So as I was looking at things that are happening around concerning COVID-19, one thing that I discovered was that I was so invested during the time that I spent almost of my time researching about trends around the pandemic, things that are happening, latest developments around vaccine development by different organizations that were leading vaccine development during the time. And one thing that I was finding out was that the virus itself was mutating at a very fast rate. Mutation basically refers to a situation where the virus changes its form. So the virus is, for example, the SARS-CoV-2, right? They have a sequence that they have based on, depending with what kind of a virus it is, it will be having a sequence that if you are to come up with a vaccine or a cure for the virus in any way, you would first need to understand this sequence, and then this sequence, in this case a spike protein sequence. After understanding that sequence and study the pattern within the changes that are happening to that sequence as you come up with the cure, then you'll be able to anticipate in a way, or before if we even get to anticipation, just by merely understanding the sequence and the pattern that is taking, you'll be in a better position to design a vaccine or a cure that can kind of address these changes. So with the rate of change that was happening with SARS-CoV-2 virus, and I remember very well when the Omicron variant came out, it made so much noise about lethality, or the how vicious it was, and it was just one of the things that got me, really interested in saying, what if we try to find a way around computational biology that can help us try and anticipate the mutational direction of how this virus is changing over time? Can we try and do that and understand how best we can, by virtue of understanding the mutational direction is following, can we try to anticipate the likely sequences of this virus over a specific period of time, such that we address the problem where instead of developing a vaccine at this particular point in time, based on the present sequence that we have, where from now until that vaccine can possibly be, get to a point where it goes to human trials, is approximately 18 months to 24 months, which is basically the life cycle of drugs between, the least you can expect, but they can go for years without even getting to human trials. But I'm saying the least that you can expect is around 18 months to 2 years, right? But with a virus, within 18 months, it would have changed so much. That's why you would realize that there was so much noise around the COVID-19 vaccines, where people really, advocates really advocated, like, there's no point in having these vaccines, because some of them were having efficacy of around 71%. The reason being, from the time they were being developed or designed up to a time where they would go for human trials, the virus would have mutated already. If the first version of that vaccine was developed against the sequence of the alpha variant or the beta variant, by the time we have the Omicron variant, that designed vaccine or drug is no longer even effective against the new mutant of the virus. So this was just one of those challenges surrounding the drug design, and trying to find a quick solution around the pandemic that was at the height of killing people, our relatives, and stuff. So this is how I came up with this problem statement and I was like, okay, let me try to work around this. I remember I was discouraged from doing this one by some of my my lecturers back then, and because they were saying this is a very big problem statement for an undergraduate degree. It's a master's level or PhD level research question, and I was like, no, I still want to explore it because it interests me. I may not be able to come up with the answer, but wherever I will leave it, right, it will be work in progress for whoever will pick it up from there, or for my further studies, or after that. So I embarked on the journey. So now fast forward, after graduating 2022 and leave it there, and here comes me in 2023 starting to have interest around putting this work out there and publishing with more information available about the SARS-CoV-2 virus, which is the virus that caused the COVID-19 disease, right? With more information, more research, more data out there to try and do further inquiry. I thought of going back and start trying to do this research. So, of course, the research question changed a bit from my initial inquiry for my undergraduate, and I started revisiting the code, revisiting the data, running some experiments. Then I realized that I think alone I was not gonna be able to really do it and come up with something that is meaningful. I would need co-founders. I mean, not co-founders, co-authors, right? To work with on this research, and that would also ensure diversity of ideas and viewpoints. So I reached out to my former lecturers and I was like, okay, can we embark on this journey together? Then yes, they were willing, they came on board, and we started the journey, right? So the first appearance of this research in terms of putting it out there and try to get input from fellow researchers, it was at the Deep Learning Indaba 2024 in Dakar, Senegal. That's when I presented this work, and I got feedback that I got from that conference, which also gave me an opportunity to to come back and make some iterations, correct some of the things that had been raised by fellow researchers, and I had hoped I would get an opportunity to also publish soon after, but things did not go according to plan during that time, and it demotivated. I mean, I waited for some time, hoping that it would get. What the efforts that I was trying to make by then to get it published would work out, but it didn't work out. I only found out after about 10 months that this is not going to work out. So it was a hurdle because I felt demotivated at that point, and I was like, let me just possibly give up on this research and just leave out and try something else. But then something kept me, actually a number of publishing opportunities and conferences came by and passed, and I was like, let me just give up on this because I didn't really have the energy and to do it because of work as well. It was just a lot to do. So until I was like, but no, this research, the sole reason why I did it in the very first place is because I wanted to have an impact in within the field, just making my little contributions. This research could be a basis of something. I know there's research, similar research around this area, but well, maybe my research could be one of the missing pieces to try to piece things together and come up with an effective methodology or approach that can help us contain, future lethal viruses that can come away, or even the present ones. Who knows? So I had to come back and I was like, let me try again working on this. Then we started the journey. I think it was now around 2025, mid 2025, actually early 2025 into mid 2025, up to a certain point. We submitted this work to one journal, and the work wasn't accepted. And we received feedback. Fortunately, it wasn't accepted, but we also received feedback as to why it wasn't accepted, which was also another opportunity to come back, work on the research, iterate, and improve on the work and stuff. And then we early this year submitted to the Journal of Applied Informatics and Computing, right, where we also initially received feedback around March. Then we had to make changes, we had to make revisions based on that feedback. We submitted again, then we received more feedback. We had to do some iterations until it was accepted and got published on the 10th of June. So it hasn't been an easy journey. It took a lot of patience, a lot of determination to put the work out there, and to get to this point where we are today. So I'm just gonna read through the abstract, then we can discuss a bit moving forward. So the abstract reads as follows. Modeling the evolution of biological sequences under temporal and probabilistic constraints remains a complex computational challenge. This study investigates longitudinal deep learning for probabilistic modeling of mutation patterns in the SARS-CoV-2 spike protein. A stacked long-short term memory, or LSTM in short, network is trained on temporally ordered amino acid sequences to estimate residue-level substitution probabilities and rank plausible future mutations. Unlike deterministic classification approaches, the proposed framework treats mutation prediction as a probabilistic ranking task, accounting for the inherent uncertainty of viral evolution. The model is evaluated using metrics suitable for imbalanced sequence data, including top K accuracy, precision, recall, F1 score, and ROC-AUC. So results indicate strong ranking performance with top 3 accuracy of 94.6% and ROC-AUC of 0.91. In comparison, the overall accuracy of 93.1% is interpreted cautiously. Please note cautiously. Given the dominance of conserved residues, error analysis shows that difficult predictions are concentrated in low frequency, rapidly evolving residue positions. Right? A comparison with a frequency-based baseline demonstrates that the LSTM captures temporal dependencies beyond static substitution patterns. Predicted mutations distributions exhibit a structured alignment with known functional regions of the spike protein, as supported by the established literature, providing qualitative biological validation. This study contributes a temporally structured and probabilistic framework for mutation modeling, emphasizing ranking-based evaluation and biologically contextualized interpretation. The findings demonstrate the feasibility of probabilistic mutation forecasting under controlled experimental conditions and provide a methodological foundation for future research on AI-assisted genomic surveillance, right? So this is the abstract of the work. So just, so that we just don't get maybe buried or end up focusing on the biological side of things, I'll touch a bit on that, but let me mostly touch on the deep learning side of things. So what you are simply saying here, there are so many methods that used to try and, lately, to try and anticipate the mutational direction of viruses, right? Some are deterministic, but when you say deterministic, we are simply more of saying there's more certainty. When we talk of deterministic, we make anticipation that is like more of certainties. But in our case, we took a probabilistic approach, because when it comes to the field of biology itself, it's a complex field that needs a lot of work, and it would be dangerous to come up with a claim that this can do that or this can do that, because it takes a lot of time, years of time of research to come up with an approach that is really deterministic without any doubt about that approach. So we decided to take a probabilistic approach based on the literature gap that we were seeing, right? And this work is not an attempt to come up with a deterministic answer that if we are to anticipate the mutational direction of viruses, here is the answer. But it was more like proving a concept of applying deep learning in terms of viral evolution prediction to see if we calculate the probability of a certain mutational direction, and can we test that concept under experimental conditions and validate that assumption, or validate that approach. So this has been the central point of this research, and we managed to prove this concept under experimental conditions with those results that I've just read in the abstract. But of course, like I mentioned earlier, such within research within the areas of medicine and biology has to be interpreted cautiously, because you can't really be certain and be so sure and make a claim, because at the end it takes a lot of time, it takes a lot of research, it takes a lot of expertise. So this was just a small contribution amongst within this vast field, where more work is needed to build upon this work, because as we're doing this work, we're building upon work done by other researchers. We made our inquiry, we came up with our findings, but it's just a small contribution towards also the massive work that needs to be done. And this could be, a starting point for someone else who wants to further inquire around this area. So maybe just going down, introduction. This is just basically talking about setting up the context, literature review, just looking at what other researchers have done and what are their findings, which is further strengthened in literature review, where we touched on viral mutation dynamics and computational model challenges, right? Which is also one of the reasons why we decided to focus on this. For example, if you read on this sentence that says the rapid evolution and adaptation of SARS-CoV-2 with the successive emergence of variants of concern, such as Alpha, Delta, Omicron, made it clear how easily it adapts to vaccine drives and community immunity, right? So we also touched on some work around artificial intelligence, applications in mutational prediction. We reviewed the literature around limitations of those existing tools that would make use of AI in terms of to predict viral mutation, right? We also touched on genomic surveillance. We also try and see. All this was in an effort to try and identify the gap that we could fit in. So you see, after all those inquiries and stuff, in response to these limitations, we tried to position this study at the intersection of temporal deep learning, probabilistic mutation modeling, and biologically informed validation, right? So, of course, we did some biological validation with our experiment, right? And like I mentioned, on some work that is out there, consider the mutation prediction of viruses as a static classification problem. But ours was an approach where we conceptualize viral evolution as a longitudinal process, leveraging the LSTM network to learn the dependencies across the chronologically ordered spike protein sequences, right? So we did that. We did look for the data. We're checking data from the GenBank repositories, the NCBI, right? So this diagram on the right, they just kind of show the architecture of the approach, where at first we chronologically ordered the amino acid the spike protein sequences, right? We did amino acid encoding, so there's that layer of amino acid encoding. Then we stack the LSTM on like different layers, and then at the end we have our ranked mutation prediction, which basically the top K, with our focus on the top 3, right? So I'm sure you have had an opportunity to look into the work and read on the approach, but I don't want to focus much on this because I suppose you have read. I want us to more like discuss this work, other than me just going through work that you have almost already read through. So these diagrams are simply just showing the findings of this inquiry, right? Then the discussion of the work here at the end. I'll also just maybe focus a bit on the conclusion, right? So just maybe going through the conclusion. This study investigated the use of longitudinal deep learning for modeling probabilistic mutation patterns and temporally ordered SARS-CoV-2 spike protein sequences. And by framing mutation prediction as a ranking-based probabilistic task rather than a deterministic classification problem, the proposed approach provides a more realistic representation of viral evolution under uncertainty, right? The empirical results demonstrated that a stacked LSTM architecture can capture temporally structured mutation patterns and produce stable probabilistic rankings across residue positions. So, of course, the accuracy of this study is high, but it is we don't attempt to use these results to be deterministic about our interpretation of this work. We interpret this conservatively, right? Due to the prevalence of conserved residues and the greater emphasis is placed on a ranking-based metrics and ROC-AUC as more informative indicators of predictive behavior. So the error analysis that we did reveals that prediction challenges are concentrated in low frequency and rapid evolving residues. Right. So maybe importantly, I can also focus on this. Importantly, the study does not claim. This is what I've also been trying to emphasize, that in our attempt, we don't attempt to claim to predict viral evolution deterministically. Rather, it demonstrates that probabilistic modeling of mutation patterns is feasible, right, under controlled experimental conditions, and can provide a structured insight into the evolution of sequence dynamics. So the proposed framework is simply contributing to a methodological foundation for AI-driven mutation analysis by integrating temporal modeling, probabilistic prediction, and biological contextualization. The proposed framework is inherently extensible to other viral genomic systems, provided that the temporally structured sequence data and domain-specific validation are available. Future work should extend this approach through comparative evolution with transformer-based architectures, incorporation of phylogenetic and epidemiological data, and deeper experimental validation to enhance translational relevance in genomic surveillance and public health applications. So, like I was mentioning earlier, we made our attempt to contribute to it, but we don't claim to be that the results are deterministic, but rather they're probabilistic, and we're trying to prove a concept that can also be applied in many other viruses that are existing or that can possibly come in the future. Right. So this is basically it about this research. So maybe allow me to open the floor for questions, or allow Sophie to jump in. I don't know how you usually do things, but maybe let me pause here and maybe allow us to interact a bit.
Yes, thank you very much, Robert, for the presentation. Your research journey is really inspiring. Following all those steps to publish this paper is really, really inspiring. I hope the other already read the paper. So if you have question, you can.
Good morning. Can you hear me, please?
Yes, we
Yeah.
hear you.
Oh, okay. Thank you, Robert, for your great work, and congratulations for your presentation. And also
Thank you.
congratulations for having, the courage to do such kind of work in a level of, undergraduate, because you mentioned it. So
Thank you.
yeah, I was asking maybe why you choose an LSTM for this task instead maybe of more recent sequence models such as transformer or state space.
Okay.
um, what will motivate the choice of the LSTM architecture?
Okay, great. I get the question. So it's also a question that I got when I was presenting the work at Deep Learning in Daba in Senegal in 2024. So you'd realize that, of course, the transformer architecture came around 2016, 2017, but it wasn't that popular. I think the transformer architecture became a bit more popular around, I think, 2022 or so, with ChatGPT first version coming out and stuff. So you see that by the time I started the work, which was in 2021, the transformer architecture was not so popular, and the approach that looked more more promising to me at that point was the LSTM approach. So of course, with the transformer architecture coming into play, over the time when I was now trying to publish, I still believed that the LSTM approach was not it's not like it was no longer really an approach that could give us the results that you can expect. So since I'd already done much work around that, I decided to continue that route and see how it would go. And yeah, it proved that the LSTM approach is still a relevant approach that you can still take. Yes, taking the transformer architecture is also another route that can be taken, but I still believed in the LSTM approach given the results that I was getting, so I decided to continue that route. But of course, I would encourage anyone who intend to advance on this work and around this field to also, explore the transformer architecture. And if I'm to advance also this work, definitely I will be trying the transformer architecture. Right? And here, even in our conclusion, we actually mention it that on the last line, when we said future work should extend this approach through comparative evaluation with transformer architecture based transformer based architectures in cooperation of excuse me, in cooperation of phylogenetic and epidemiological data and a deeper experimental validation. So what we're simply saying here, we're saying that we didn't do all the work that needs to be done. There are still other approaches that we can try and make and compare the results with the findings of this research, and then in an attempt to advance the work. So of course, there's still a lot of work to be done. The transformer architecture is one of the approaches.
Yeah, perfect. So I think it can be, interesting to compare, your work maybe against transformer based architecture, like you said. So um, that's clear there. Thank you.
And thank you again for that great question. It's really a great and an interesting question. Yeah, I do concur with you that we can also try other approaches and compare the findings. And like I mentioned, if ever I'm to advance this, as I am starting my master's journey, if I'm to find myself also still curious about this area, I'll be exploring the transformer architectures and see what would be the findings. It would be also interesting also to build up on this work. So yeah, thanks again for that great question. Any other questions or contributions? Any other questions?
Maybe if you don't mind, maybe in the modeling part, can you come again maybe quickly how you did, which approach you choose maybe for splitting your data into training and testing set? Did you make sure that the future sequences was never used during the training?
Okay, yeah. Now we did a bit of work. Actually, we did work around that in our data preparation. Let me try and go to that part. I hope I'll easily find the part where we did that. So this is the part, but the part that I want.
Yeah.
Then
Yeah.
yeah. So this part, you see, we of course we did a bit of work first to try and process the data itself before we even feed it within the module, right? That is just checking the quality of the protein sequences that we have. Those that were incomplete, that had like some missing amino acids, we were dealing away with them. So Yeah, so we also we did filter for quality and completeness, and we had also to order the sequences chronologically based on the like which sequence came first at what point, which one came last, because in a way this was trying to also make sure that, I think if you can see here, we mentioned it here. I think it also answers the question that you had. Like temporal dataset partitioning ensured that future sequences were not used during training, thereby preventing information leakage and establishing realistic evaluation of mutational and forecasting performance here. So in terms of our data size and the splitting that you also asked, our data at the end consists of 52,314 spike protein sequences, and these were spanning between January 2020 and June 2024. And we did all the alignment that is needed in terms of positional consistency and stuff. And our split, we took the 70% for training, 15% for validation, and 15% for testing. So that's how we split our data. So I hope that answers your question in terms of data preparation and preventing data leakage.
Yeah, sure. Thank you.
Yes, I think Ngwaro's hand is up. Yes, Ngwaro, please go ahead and ask your question. In case you are speaking, Ngwaro, you are on mute. We can't hear you. Ngwaro, if you are speaking, we can't hear you. I see your hand is up, but we can't hear you speaking. Okay, thanks for the compliment, Ngwaro. Okay, maybe you can put it in the chat, then we can get your question. Meanwhile, as we wait for Ngwaro's question, does anyone else has a question that we can try and address?
Do you have questions?
Yeah, maybe if you don't mind waiting, Guaru. I understand this work was more about temporal modeling. So I was wondering, maybe also considering, special dependencies can also contribute to the result. Maybe including geographical information, since mutation dynamics may differ across regions or countries. I don't know if it aligns in your the perspective of your works,
Yeah.
or
So, of course, the findings with the data, you would see that the mutational patterns of of the sequences collected in areas around the United States and other places, as compared to the African region, would be different in a way. So, but we didn't really focus much on that in this research. But the good thing is, lately I've been also involved with climate sensitive infectious disease network, which is also focused on diseases modeling, with also much emphasis on the such factors such as geography, climate and stuff, all those different factors. So it has also enriched my perspective as to the many factors that are involved in that also affect like disease or viral mutational directions and stuff. So it's also, those are also factors that I would encourage anyone who wish to advance upon this work to also look at. And as I mentioned, if I'm to advance this work, those are some of the things that I would incorporating alongside taking the transformer based approach.
Yeah, exactly. Thank you for that.
And thank you again for your questions. I mean, your questions makes me curious. Like, are you really in this field? What's your background?
Yeah, my background is more about mathematics, so but I have interest on doing research on
Great.
special temporal downscaling for some climate variables. So looking at your work, so this is more about temporal, but I think also we can considering the spatial learning, the spatial patterns can also help the model. So I'm not really about I didn't do great thing on that, but theoretically I think that can be valuable.
Okay.
So yeah, that was where my curious was. But I
Yeah.
will be very interested also on working again or um,
Yeah.
trying to consider that special part of the work.
Yeah, I really like your perspectives and your contributions. If it's an area that you are really interested in and curious about, I would be happy to explore any form of collaboration that you can take because in as much as I did this work and put it out there, like I said, it's an area that is still interesting and dearly to my heart that I'm most likely going to continue, building upon this work as I embark on my master's journey. So, if it's work that really resonates with you, we can explore collaboration for further work around this area.
Yeah, exactly. I think we can try to to challenge that part of the work. I
Yeah,
mean, learning the spatial pattern on that.
yeah. So,
But it's perfect. Yeah, yeah. I got I get your LinkedIn.
okay, no worries. Yeah, I just pasted my LinkedIn in the chat for in case we are or like for those who are not we are not connected to. But yeah, I think I can also get your contact from Sophie. Then we can talk further and try to explore what we can actually work on together. Any other questions, Kwaru?
Yeah, so Robert, I hope you can hear me.
Yes, now I can hear you clearly.
Okay. Yeah, I was just having a few challenges with my microphone.
Okay.
Um, yeah, so I think my question is almost similar to something that has been already discussed. Given
Mhm,
that long short-term memory models, they suffer from this challenge of vanishing gradients or
mhm,
exploding gradients.
mhm,
And if you look at the spike protein
mhm,
of COVID-19, previously called SARS-CoV-2,
mhm,
it's like almost like 1,100 something amino acids.
I mean,
So
yeah.
that's a very big sequence if you think about it.
Mhm,
And if we look at the formula you shared,
mhm,
it takes it in the previous sequence
mhm,
at time t, and
mhm,
then predicts uh, the amino acid at position I
mhm,
at time t+1.
mhm,
So, given that it's taken this big sequence,
mhm,
it probably will have some kind of impact
mhm.
on the prediction. So my question is, did you do any kind of feature engineering to try and shorten the sequence, or do anything to try and make it better, make the model better, or you just take the sequence as it is and you give it as those are the features which the model makes the prediction on?
Okay. So we didn't.
Then also,
Okay.
just to add it, that's why I guess the earlier speaker mentioned that then transformers are better because then they have this ability to use long range dependencies to make a prediction.
Yeah. Thank you so much for that question. I mean, it's a great question. It's a great contribution. Yeah, we didn't do a bit of, work around trying to maybe shorten the sequence, because in a way we thought it could possibly affect also the performance itself. So we really didn't do. We were just like, also as I mentioned, that we were also checking for completeness in our as we were doing our data preparation, data quality check. So we really took the full sequences. Anything that had some missing is missing and stuff, we really didn't do that, and we didn't try to do feature engineering to try to come up with maybe shorter sequence and stuff. We just took things as they are. And I do agree with you that the LSTM really suffer when the sequences tends to be longer, which is actually an advantage that the transformer architecture has. So yeah, I think it's an opportunity there to further this work. It's an opportunity that I'm also still interested in exploring and seeing. For anyone interesting, they're welcome. We can embark and start on that journey to try and take the transformer approach to try and see what will be the outcome of this. But I'm confident that the transformer model, the transformer architecture, will significantly come up with findings that we can that could be better than these findings. So we can build upon this work and further that using that approach. I do agree with you on that one.
Yeah,
But,
thank you, Robert. Then also just to probe your mind, what I guess maybe because I was out a bit, maybe it's something that you're already discussing. But what do you think? Because there's COVID was just a problem that happened over maybe 3 years, and no one talks about COVID now. But in Africa, we've got this challenge of HIV, and HIV has been around for a long time. Initially, we didn't have any treatment. Now we have got treatment. But the biggest challenge with treatment is resistance, and this resistance to treatment comes because of mutations in the HIV protein, whether it's mutation of the protease or the reverse transcriptase, and it's a challenge we have. And I don't know what you think. Do you think similar models could be used in either research in silico or in clinical studies, or maybe further in the future they could actually be basis of choosing medication for patients?
Okay. Yeah. Yeah, I really believe in the potential of these approaches in terms of I do agree with you. Like nobody talks about COVID now, but we still have long-standing problems that we've had, like with the likes of HIV and stuff. So we also mentioned a bit about it on this week, where we say this was our fourth like recommendation, where we said expanding the proposed framework beyond SARS-CoV-2 to other rapidly evolving pathogens, including influenza viruses, HIV, and emerging zoonotic threats, would provide a robust test of generalizability and scalability. So cross-pathogen evaluation may also review shared evolutionary patterns and pathogenic specific constraints, thereby contributing to the development of more universal mutational forecasting methodologies. So it might not be drag and drop, or not drag and drop per se, but fit and go approach, because of course the characteristics, or should I say the behavior of these these viruses tends to be different in a way, but I think the underlying concept or the underlying idea can still be applied to these other viruses, HIV included. So yeah, that's an interesting also finding. Like I was saying, if I'm to probe this further, definitely I won't be applying this to SARS-CoV-2, but also identify another virus that I can try to apply the transformer architecture in, most likely HIV. Yeah. So that's really an interesting contribution, and I know you have so much background around work in HIV, so it's an area that we can also try to explore together and see if we can apply the same approach in HIV and see what would be our findings. But it's an area that I'm still interested in and that we can explore. But yeah, thank you so much for the question and for the contribution. Ngwaru is no longer with us. He's with us. Okay. Thanks again, Ngwaru.
Thank you, Robert, for the answer.
Okay, great. I hope it answers the question, though. Any other contributions, Tim? I'm gonna call out names now and have everyone say something, because we're a small group and it would be great if everyone just ask a question and make a contribution.
Yes, we don't have many persons, so we can discuss each other. I have one question.
Mm-hmm.
COVID already passed, so can we use this paper to another subject, to applicate it to another virus?
Yeah. So thanks so much for the question again. That's a great question. I think it's almost the same as the question that Ngwaru asked as well. So yeah, I still believe that the underlying approach is still the same. This approach of we can take the lessons that we have learned from this research, as well as the gaps that we are already identifying in this research, the likes of maybe the length of the sequences, as Nkwaru mentioned, vis-a-vis the approach of LSTM. So those are some of the gaps that we are already seeing and maybe learning from out of this research. So I think we can carry those lessons with us and try to use the same approach on a different virus other than the SARS-CoV-2. So that we focus on maybe viruses of concern at this particular point in time, or viruses that we anticipate to cause problems in the future. So yeah, so the short answer is I think we can still rely on this approach in applying it in other viruses. Yeah. I see your hand is up, Sophie. If you want to say something.
No, thank you very much for the response.
Thanks again.
So can we come on the result you have, comparing on other result on internet?
Please come again.
Can you come on the result you have comparing to others we have in internet in other research?
Yes. Yeah, we did a comparison of our findings against the other literature that we looked at. Of course, with some the findings will be the same. The results. With some, our results are a bit higher than others, but at the end, it also comes back to the differences in the approaches taken. For some, they take a deterministic approach. For us, it was a probabilistic approach. So at the end, that also, in as much as we can possibly also compare the results, those factors also needs to be considered as to the differences in approach.
Okay, I see.
Yeah. Any other contributions, questions? Yeah, I think in the absence of questions, maybe I'll hand over the mic to you, Sophie.
Yes, nobody have another question. So we will end up here the reading group. Thank you very much, Robert, for coming. That was very interesting. That was very interesting, and the discussion, the interaction with Pap Malik and Goa was really interesting. So thank you. We hope we will have you next time.
Yeah, let me say also thank you, Sophie, for and the entire group for having me. Thanks, Sophie, for extending this invitation to me. It's been a pleasure interacting with you this evening and discussing this work. I loved this experience because ever since this work has been out there, this was the first time I had an opportunity to discuss this work like with a group of people. You know, now reflecting, looking back, and to hear feedback about. I mean, what has been their experience in reading this paper? What are some of the gaps that they've been finding, and what ideas do they have around this research? Which is also an opportunity to learn from this and start thinking around, okay, what can be done further around this work. If I'm to further this work, what is the starting point, where to start from, what can I possibly look into? I think this also session also served as an opportunity for us to just identify common areas of interest that we can possibly work together and further this work. And who knows, maybe we are sitting at the center of I mean, we hold the potential to actually come up with something that will address some of these problems that we have in biology and medicine. So above everything, thank you so much for the opportunity, and thank you so much for having me.
Thank you so much, Robert. I can't pronounce his name, but he sent her LinkedIn account in the chat so we can connect each other on LinkedIn. So
So
thank you
I'll help.
so much.
Yeah, I'll help you guys. I know you're francophone, and the name is actually uh so it's Ngwaru.
Wow, okay.
So it's
Thank
Ngwaru.
you. Thank you.
Ngwaru, yeah. So yeah, Nkwaru, maybe just an opportunity to also talk a bit around this. So with Nkwaru, I was actually surprised to see him here, but we worked together for about 2 years when I was based in Eswatini. We worked together there, and yeah, it's been interesting, and I mean interacting with him here and seeing him here. I was happy to see him here because I mean I've had an opportunity to work with him, interact with him. I know he's someone who I mean takes his time, I mean, and passionate about this area. And I know that I knew that I would expect great lessons from him around this area. So I was happy and to see him here, but I knew that at the end our discussion and our conversation would be great, with different perspectives and the likes. So thanks, Ngwaru, for coming, and thanks everyone for coming. And over back to you, Sophie. Thanks for the invitation.
Thanks,
I
Robert.
yeah.
See
Thank you so
you
much,
later
and good. Yeah,
on next paper reading.
thank you so much.
L'enregistrement est arrêté.